I'm gonna wait a few seconds to let people come in, and then we're gonna start. Okay, so let's start. So welcome everyone, and congrats for making it already to half the session for this session on vector-borne and zoonoses. So as you can see, you're already at the half. So congrats for this, and thank you for staying with us. Regarding these session learning objectives, a little reminder. So these are to identify the connection between habitat and biodiversity loss, climate change and infectious disease, to explore how climate change is leading to increased risk vector-borne and zoonotic diseases and their distribution patterns, to discuss the impacts of temperature and climate modification to vector, reservoir, and pathogen life cycles, and to learn about health system adaptation actions and possibilities, such as early warning systems and preparedness, prevention, response, and recovery plans across organizations such as the ECDC. Regarding the logistic, now you know everything about logistics, but we have a 90-minute session. They will be recorded and posted on the website, and all the referential material and slide decks will also be on the website. Regarding the certificate of participation, like I'm not going to repeat, but when you have 70% of attendance, you will get it depending on the answer to the survey at the end of the class. And today we're going to have three presenters, Professor Giovanni Rezza, who is our lecturer, and Professor Polychronis Kostoulas and Professor Chen Semenza that are doing the case studies. I'm Nabbe. I'm an ASPHER young professional, and I'm co-moderating with Tara, who will present herself later, but she's an ASPHER fellow for climate and health. And I also work at the European Hospital and Healthcare Federation. So now to introduce Professor Giovanni Rezza. He's a specialist in hygiene and preventive medicine and in infectious disease. He has been the Director General of the Health Prevention Directorate at the Italian Ministry of Health and the Italian Chief Medical Officer. He is now a professor of hygiene and public health at the Vita Salute San Raffaele at the University of Milan. Sorry for my Italian people. His area of expertise includes HIV and emerging disease, such as chikungunya, West Nile virus, influenza, coronaviruses, monkeypox, and all great things. So I will let you the floor, Professor. Thank you.
So thanks, first of all, thanks for inviting me. It's a real pleasure to give this presentation also because I'm really investigated several outbreaks, especially outbreaks of chikungunya. And in particular, the first outbreak, it occurred in Europe. That was a large one in 2007. So I will discuss about the outbreaks we observed, the situation in Europe, and also I will give you some insight on the introduction and establishment of tropical mosquitoes in temperate areas.
Professor,
yes,
could you pass
yes,
in presentation? Thank you.
Yes. Can you see it now? It's
perfect.
Okay. I want to start from something that occurred about 1 century ago. And that is really something very interesting from my point of view. Actually, dengue outbreaks were used to occur in Europe and we had several outbreaks actually in 1889, 1895, 97, and also at the beginning of the last century in 1910. But there was a big epidemic actually occurring in Athens and in the Piraeus in 1927 and 28. Big outbreak of dengue. The first wave that occurred in 1927 was a mild wave. So the clinical presentation actually was mild, like in primary dengue, and it occurred in the early fall of 1927. Then there were sporadic cases occurring during the winter and during the springtime between 1927 and 28, and there was a severe wave then in August 1928 with more than 650,000 cases, and also with hemorrhagic manifestations. And so also that's about 1% of those of people more than 60 years old actually is estimated that died. So probably there was a sequential circulation of different dengue serotypes, like dengue 1 and dengue 2, even if there's no definite evidence about it. But the hemorrhagic manifestations actually stand for secondary dengue, so a secondary dengue event. The important things to say is that the epidemics in 1927-28 were sustained, were transmitted by, the virus was transmitted by Aedes aegypti, that is the classic, the traditional tropical mosquito. Then minor outbreaks occurred over a few years, but Aedes aegypti disappeared from the Mediterranean area after 1930. So no cases of autochthonous transmission, of local transmissions, were identified anymore for more than 80 years. So that's important because it means that actually the tropical mosquito, Aedes aegypti, had the climate suitability also in Mediterranean Europe, even though then it disappeared for some reason that we actually don't know. But I want to talk about the return of tropical diseases that we observed in, especially Mediterranean Europe, in the last few years. And I think the chikungunya case study is very important from that point of view. The story starts in about in 2004, when a big epidemic ravaged the coast of Kenya, a big epidemic of chikungunya. Then chikungunya moved through the Indian Ocean islands, causing a lot of cases in La Réunion, and then in the other islands of the Indian Ocean, reaching India in 2006-2007, and causing more than 1.5 million of cases in the Indian subcontinent. It was the end of August of 2007, when I was just back from my vacation. I was in Rome and was very hot, very humid. And I received a telephone call from Ravenna. You see, Ravenna is in the northeast of Italy, not far away from the Adriatic coast, near Rimini. And they said, you know, we have tens of cases of fever. That was quite strange because, you know, having an outbreak of fever at the end of August without diarrhea, without gastroenteric manifestation is not usual in our country. And there were newspapers saying, you know, there is an alert, and because there are many cases of fever, and this fever maybe is due to Papadaci. You know, the Papadaci fever is due to the so-called Toscana virus, the Umea virus causing fever and sometimes brain manifestations. But it usually causes only sporadic cases near the mountains, near the Apennines, especially in Tuscany, and some cases also in Emilia-Romagna and in the Marche, in the in central Italy. But it's not used to give outbreaks. So for that reason, I said, wait a minute, tomorrow I will come and see and try to understand what is happening actually in nearby Ravenna. So we went to the epicenter of the outbreak. The epicenter of the outbreak was Castiglione di Cervia. It's a small village, just 2,000 people living there. And there's a small river, and on the other side of the river, another small village, Castiglione di Ravenna, with other 2,000 people living there. And we went there. Actually, I'm the guy in the center. I was younger at the time. I'm the guy in the center of the group, and there were with me some entomologists and the regional health authorities and the health authorities of the district, the health district of Ravenna. So we went in this place. There were stands of cases of fever. We had to understand what was happening there. So we started the investigation. I saw some patients, visited some patients, and the patients had actually very high fever usually, and very strong and long-lasting joint pain. One of them was an old guy. He said, I've been in concentration camps during the Second World War, but I'm suffering now. I'm suffering more than when I was in these concentration camps. Just to give you an idea of the strong joint pain, long-lasting pain resistant to anti-pain drugs. And about half of them had also skin rash, itching skin rash. But the strong pain, joint pain, was the main symptoms together with the fever. So the entomologist tried to understand what was happening, if there were possible vectors, and they tried to detect these vectors, especially in the small residues of water, and they say, here there are no papadaci at all, for sure, but there are a lot of larvae and also adult mosquitoes, and all of them are Aedes albopictus. Aedes albopictus is the Asian so-called tiger mosquito. And Aedes albopictus has strange attitudes, and behaviors. It's very, very lazy. It doesn't move more than 100 meters, 150 meters away from the vegetation, lives in the vegetation. It usually bites early in the morning and during the evening, not during the hot hours of the day, not much actually. And so they say, there are more Aedes mosquitoes than air actually in the atmosphere. So it's the situation was quite bad actually. You see, this is the sort of natural experiment of what can happen when a tropical virus is introduced in a temperate area, in a new area where all the population is naive, is susceptible. And you see the first case occurred here nearby the river. And actually it was an Indian family. So I went to visit the Indian family and asked them, of course, if they have been in India recently. They say, no. None of us has been there. And that was quite strange, actually. And it was not a coincidence that the first case occurred in an Indian family, but at the same time, they never moved in. They didn't move in. They had not moved in the last couple of months. So, you know, how was the virus introduced in the population? You know, it was quite difficult to imagine. But a young guy in the family said, you know, all of us have been with fever, of course, at the beginning of July. But we received a visit from we had not been in India, of course, but we received a visit of my uncle that was used to live nearby. And when he came here to visit us, we had dinner together outside the house. And he had a very high fever during the evening. So probably he was viremic. He was bitten by a lot of mosquitoes, and the mosquitoes amplified the virus and then started to transmit the virus to the other members of the family. I will show you the epidemic curve that is really impressive from this point of view. Then, you know, the other cases, clusters of cases occurred in Castiglione di Cervia, in the same village, but then also in the other village, Castiglione di Ravenna, because as I said before, you know, the mosquitoes are lazy, but people's mobility is very high. So there were people coming from Castiglione di Ravenna going to the affected village and bringing back the virus with them, for sure. Or otherwise, you know, the mosquito may enter a car and go to other places. Then there were also clusters of cases in other places, in other towns nearby, quite nearby, you know. And then we had also some cases in Bologna that is quite far away. That's very interesting, but was a family that probably traveled to Castiglione di Cervia, to the epicenter of the epidemic, and brought back the infection with them to Bologna. This is the epidemic curve. You can see that the green bar is one case, we can call it case 0. And then the index case, case 0 occurred on 23 of June, was the guy that came back from India, from Kerala, that is in the southwest of India, where there was an epidemic, or big epidemic of chikungunya at that time. And then you see at the beginning of July, actually, after the amplification time of the virus in the mosquito and then the incubation time in the human, we have the index case that is one of the family members of the Indian family. And then you see that there's the epidemic curve rises in a very sharp way, then it reaches a peak. And at this time, there's also mosquito control intervention. And then you see that the number of cases starts to decrease quite dramatically. You see, we had secondary clusters in Cervia, that is 9 kilometers away, with 19 cases. Only 9 cases in Ravenna, that is 23 kilometers away, and other small clusters in other cities or towns like Cesena and Bologna. And 6 cases also in Rimini, that is 49 kilometers away. So it's because of human mobility, not because of mosquito mobility, of course. Oh, we had also the so-called litmus test. In Italy, we say la prova del 9, the proof of 9. There was, the virus was sequenced, and the phylogenetic tree shows that the virus from Ravenna, from Italy, was very, very, very similar to the Indian virus circulating at the time in Kerala. So for sure, this means that the virus was introduced by the Indian guy, and then it spread because of the presence of active presence of competent vectors, that is Aedes albopictus mosquitoes in Italy. I have to say that Aedes albopictus mosquitoes were introduced in Italy in the beginning of the 90s, and Italy was the first country to in which the tiger mosquito, the Asian tiger mosquito, established. But then it established also in Albania and on the coast of the Mediterranean basin. Then we'll see what is happening now in terms of the distribution of the Aedes albopictus mosquito. We also conducted, after a few months, seroprevalence surveys showing that at the end of the outbreak, about 10% of the population had been infected, they had antibodies against chikungunya, and the prevalence of antibodies tended to increase with age, with increasing age. This is because usually people very old, they don't go to the beach, they stay in the village, and during the evening they are in front of, they stay in front of the house, you know, just outside, waiting for mosquito bites, actually. And males had the higher risk of being positive than females. This is probably because males are not used to stay, old males are not used to stay in the kitchen, but just, you know, losing time, wasting time in front of the house. So everything has an explanation in terms of behavior, I think. Then 10 years later, something different occurred, but different, but very similar. We didn't have cases of chikungunya for 10 years, but then it was again at the end of August, 1st of September, and there was a colleague from my institute. At that time, I was working as head of the Department of Infectious Diseases at the Istituto Superiore di Sanità, that is the National Institute of Health. And a colleague came and said, you know, I'm just back from my vacation on the beach in a place called Anzio, that is about 50 kilometers far away from Rome. And she said, you know, and all my family has fever. I say, no, it's okay. But there are other people with fever. Yes. Oh, on the beach, you know, everybody had the fever, you know, a lot of people at least. And it was August. Again, the symptoms were fever and joint pain. So I said, oh, maybe this could be something like chikungunya, maybe dengue, who knows? And I say, you know, asking her to have some blood samples. And after one day, actually, the diagnosis was done, and actually was chikungunya. And there was actually quite big outbreak in Anzio and other villages on near the beach. And then, you know, people came back at the end of August, tended to come back to Rome from their vacation in Anzio, and there were several clusters of cases also in Rome. It was quite scary because, you know, we didn't know what can happen when a tropical virus reaches a big city like Rome. And actually, there were clusters of disease, but there was not a big epidemic, fortunately, maybe for two reasons. One, okay, there were mosquito control interventions. The other one is that the urban setting is not as favorable as the rural setting in terms of vegetations. So, you know, mosquitoes had to move from the first to the fifth floor. Maybe it's, you know, it's a little bit complicated. and you don't live outside very much when you are in a big city, at least in our temperate areas, and also it was September, and on September there are still a lot of mosquitoes around, but the autumn is quite near, it's going to come. So there was not much time for the outbreak to go ahead. But we had the secondary outbreak. That was very interesting, because it's one of a few examples of the secondary outbreaks we had of a tropical virus in Europe. And the outbreak, this secondary outbreak with more than 100 cases. Overall, the cases were more than 500 actually. But this outbreak of more than 100 cases occurred in Calabria, the Ionic coast of Calabria, so in the deep south of Italy. And it was caused by a guy coming from Anzio, from the Lazio region, so near Rome. He went to this village called Guardavalle, and it started a transmission chain. And actually, there were really many cases. The population was quite scary, and we had to guarantee, to ensure some assistance to both doctors and the population there, But the outbreak then, was stopped thanks to mosquito control intervention. That was quite strong. And at the same time, also because the autumn came and the activity of the mosquitoes was already reduced. During those years, from I would say between from 2007 to 2017, there were also cases of chikungunya due to local transmission, so transmitted by Aedes albopictus. Also in southern France, you see 2 cases in 2010, 12 cases in 2014, 17 cases in 2017. So just sporadic cases of local transmission or small clusters. And they were very smart in detecting them, I think. So the surveillance activity was very, very, very active and efficient, first. Second, the idea is that local transmission is more common than we can think. But the R0 of the virus tends to become, to remain low unless, unless the chains of transmissions multiply and become quite long. When the chains of transmission, when you have several chains of transmission and long chains of transmission, R0 may become more than 1, and the outbreak may start. So in conclusion, with regard to chikungunya, we can say that several chikungunya clusters cases and outbreaks occurred in the Mediterranean areas in a 10 years period. Because of the presence of competent vectors, this is always possible, but you need a synchronicity between epidemics in the tropical country and the hot season in temperate areas, unless there is no major climate change. So it's important to improve preparedness and response to chikungunya outbreaks, for sure, in areas with high density of Aedes albopictus, and in mosquito control interventions are, of course, very important. And at the same time, also, we may start to consider reactive vaccination cases of in case of bigger outbreaks, now that chikungunya vaccines are going to become available. But dengue also is back. I started this presentation talking of the dengue outbreaks in Greece, in Athens and Piraeus. But actually, in the last few years, we observed several cases, sporadic cases, clusters, and small outbreaks of dengue again in Europe, especially Mediterranean Europe. You can see all the series of cases. This is from the ECDC. 2 cases in Nice, so south of France, in 2010, the Bouches du Rhône. Many cases, actually, many sporadic cases or just small clusters were observed in southern France. Then there was probably a bigger outbreak in Korčula Island, so in Croatia, near Dubrovnik, actually, in mid-August 2010. That was actually was detected because a guy from Germany going to spend his vacation. He went to spend his vacation to the island of Korčula. He went back to Germany. He had high fever, retroorbital pain, and he was diagnosed with dengue. And then a seroepidemiological survey was conducted in Croatia, and they found actually 5% of prevalence of antibodies against dengue in that area. This is quite high, of course. It's not explained. It may not explain by travels in other countries. Then there was a big outbreak in Madeira, but that was due to Aedes aegypti that is present in Madeira. Madeira is politically belongs to Europe because it's Portugal, of course, but from the geographical point of view, it's very different from the Mediterranean area, for sure. And also the vector, so it's different, not Aedes albopictus, but Aedes aegypti. Then we had 11 cases in Veneto, in the northeastern of Italy, in August 2020. Nobody reminds it because we just had the first dramatic wave of COVID at that time. And then other cases in southern France, especially in the summer of 2022, actually, 65 cases belonging to different chains of transmission in southern France. This was quite a major event, actually. And then last summer 2023, 2 cases in Marseille. But last summer, we had many cases of dengue, actually, in Italy, in 2 regions, in 2 different regions. In Lombardia, especially in a place in a small village called Castiglione, but it's Castiglione not Castiglione di Cervia, it's another Castiglione. And also in Lazio, we had 2 different transmission events in Lazio, one in Rome and one in Circeo. That is a beach venue about 100 kilometers away from Rome, and with a total of about 80 cases of local transmission, due always again to Aedes albopictus. And what is impressive is that actually there were multiple introductions with different transmission chains in different regions, like something is changing. Maybe there are more larger epidemic in places like Brazil, where there are many tourists coming from Italy that may bring back infection with them. And also climatic condition may explain why the probability of these events appears to increase. So with regard to dengue also, what we can say that small dengue outbreaks are relatively common events that when you have several cases, maybe they can be also due to multiple introductions of the virus. Usually these outbreaks appears to be self-limiting, maybe because there's a lower vector competence of Aedes albopictus compared to Aedes aegypti when we get to dengue. This is a possibility. Actually, experimental studies that we are doing show that Aedes aegypti is a better has a better vector competence than Aedes aegypti, and is a better vector for chikungunya than for dengue. Also, in the case of dengue, now we have vaccines with a high efficacy. However, they may not protect against all the serotypes, but reactive vaccination is a possibility when mosquito control interventions do not work. But due to the self-limiting nature of these events, up to now there was no need for reactive vaccination. So it's important now to understand what may happen in the near future. We need to update our terminology in order to describe the distribution status of Aedes species mosquitoes in Europe. We talk about the establishment, an established population when there is an evidence of reproduction and overwintering, or that's mosquito species, and that is observed in at least one municipality within the administrative unit. We talk about introduced mosquito when the species has been detected, but without confirmed establishment within the administrative unit. So a mosquito can be introduced, you find the mosquito, you say there's been an introduction of the mosquito, but if there's no reproduction, there is no overwintering, we cannot talk about establishment of the mosquito. And then we can say a mosquito is absent, mosquito species is absent just if field surveys or studies of mosquitoes were conducted, because otherwise we had to say we have no data or the distribution of these mosquitoes is unknown. And I had to say that actually that the distribution of Aedes albopictus now in Europe is quite impressive. The Aedes albopictus not only is established in all the Mediterranean area, you see Italy is completely red. There are Aedes albopictus, there's Aedes albopictus in all the sites, with the exclusion of some area of the Alps, for sure, due to the altitude. And but also you see Aedes albopictus is established in the Balkans, in the Balkan areas, on the coast of Greece, Romania, but also in the inland, in Croatia, Slovenia, southern France, Mediterranean Spain, the south of Portugal. But what is interesting is that now the mosquito has been found and is established also in France, in the area of Paris. There was this infestation, mosquito control activity last summer when a case of dengue came back a patient came back with dengue from an endemic area, and for the first time in Paris, it was implemented mosquito control activity. So there's a spread toward Central Europe, maybe toward Northern Europe, of Aedes albopictus. You see that only a few years ago, actually, the mosquito Aedes albopictus was present only in most of Italy, in Albania, in some areas of Croatia and Mediterranean Spain. But the projections, the predictions say that on the basis of climatic suitability, actually Aedes albopictus may go to be established also not only in Central Europe, but also in some areas of northwestern Europe. The other interesting thing is about Aedes aegypti. Actually, I did some studies in the area of Sochi years ago in the Caucasus, and we found that Aedes aegypti was established there. We are talking about 2013, 2014, those years. And Aedes aegypti is present also, is established also maybe in Georgia, in the northeastern Turkey, and now also on the coast of the Red Sea in Egypt. But for the first time, the mosquito, Aedes aegypti mosquito, is established also, is proved that it is established in a European Union country, in Cyprus. So is Aedes aegypti coming back to the Eastern Mediterranean? So this is the main question. We have to wait and see, actually. I hope it won't happen, but it's it's a possibility, especially if the winters are becoming less cold, actually. So we can say that this is from the European Center for Disease Control Stockholm, that since the previous update that was done in February 2023, in last summer, there were main changes with Aedes aegypti that was found to be introduced in the Spain Canaries and established, so in several places, but especially in Cyprus, with a further spread in Egypt on the Red Sea coast, and Aedes albopictus that is established, for example, now also in some sites in Algeria, with additional introductions and establishment in Austria and in other places. So, sorry, this is a mistake. Introduction in Cyprus is referred to Aedes aegypti, not to Aedes albopictus. Please correct the slides before we have to correct the slide before distributing it, before sharing it. So what are the key points, the final key points in coverage? So the take-home message is that the tiger mosquito, so Aedes albopictus, is going to spread toward Central and Northern Europe. And what happened in Paris last summer is very clear to this regard. Aedes species other than Aedes albopictus also tend to be established in Europe, so Aedes aegypti in Cyprus, but also Aedes coraigus that is being found also in northeastern Italy, for example, but also in other Central European countries. However, we have to say that Aedes aegypti is less resistant to frost than Aedes albopictus. Thus, it means that actually overwintering of this mosquito is more difficult. But if climate change continues in this way with very mild winter, it may become the establishment of Aedes aegypti in other European countries may become, especially in Mediterranean area, may become a possibility. Of course, large outbreaks may occur in case of early introduction of a tropical virus in the hot season. If, for example, the virus is introduced in June, it has a lot of time to produce a large outbreak than if it is introduced at the end of August, for example. But there are prolonged, the prolonged hot seasons actually due to climate change may increase the possibility of larger outbreaks. Caveats, Aedes aegypti is a better competitive vector than Aedes albopictus for dengue, for example. So in this case, we can't expect larger dengue outbreaks unless Aedes aegypti is established in European countries, but I think we need more definitive results about it from experimental infection of mosquitoes. And the final question is endemization possible as a consequence of prolonged hot season? I think this is the main question and the main, it needs an answer that we cannot give yet at this time. So thank you for your attention.
Thank you, Professor, very much for this interesting presentation. So we have time for at least one question. So we have one from Emin Didem Evskikirats. Sorry if I mispronounce your name. Do you have any early warning systems that deliver warning messages to each individual living in cities, disaggregated according to age, gender, residence, diseases, or risk for vectorial disease in your region?
No. There is a national plan for sure for the control of vector-borne infections that includes, of course, all infections due to dengue, chikungunya, West Nile, and the other viruses. And also there's much importance, a big importance is given to the distribution of information, providing information to the regions and also to the population, but not targeted information to specific groups.
Thank you. So I have another one for you. From Arne Ulig, what are the biggest challenges to deal with invasive mosquitoes and the spread of tropical diseases in Europe? And do you think the One Health approach is suitable to deal with those issues?
But the One Health approach, you know, it seems to be quite a slogan sometimes, but at the same time, it's something very, very important. If we neglect the slogan, and if we look at the very concrete things. For example, I had to say that in Italy, the One Health approach is a very ancient one. Why? Because we have both the vet and the med sector within the Ministry of Health. In some countries, for example, the vet sector is in the under the Minister of Agriculture and not under the Ministry of Health. Of course, this means that the vet and the med people had to work together. And vector-borne infections are classical examples of the importance of this One Health, even though, you know, I'm in some way, I don't like slogans, but in this case, I may say that One Health is important for this reason, yeah.
Amazing. Thank you very much, Professor. Then I will leave the floor to my co-moderator, Tara Chen, to introduce the case studies.
It's a pleasure. Bye, ciao.
Bye-bye.
Thank you so much. So I'm excited to get into our case studies. So our first case study will be presented by Professor Polychronis Kostoulas, who is an associate professor of epidemiology and the head of the Laboratory of Epidemiology, Artificial Intelligence, and Biostatistics at the Faculty of Public Health in the University of Thessaly in Greece. So Polychronis, if you want to share your screen, we're very excited to hear from you.
Thank you, Dara. Yes, I will. I'm going to share my entire screen. Hopefully this will work as it should. Can you see my screen now? Yes, I hope.
Yes, and if you can just put your presentation into presentation mode.
Okay.
Perfect. Thank you.
Right. Can you hear me well?
Yes.
Okay. Thank you very much. Thank you very much for the invitation, Tara. Nice meeting you today, and I would like to briefly talk about what we have in Greece in relation to climate change. First of all, I would like to say that I remember as a kid that we didn't have tiger mosquitoes in the past, and there was one summer, I can't recall when exactly, that we first saw a tiger mosquito while we were on holiday with my family, and we were terrified. And then year after year, we became it was so common, and now it has been, as we saw in the previous talk, it is now common in Greece along other countries in the Mediterranean, and of course we're very, very familiar with it right now, and every summer we see tiger mosquitoes along with other mosquitoes that we have. But it was very striking in the past that a new mosquito came, and I really remember this moment, which means, of course, that the tiger mosquito came in Greece and in the Mediterranean with transportation, but it was established because of climate change, and this is something that was in my mind in the past, and obviously is an indirect indication that we have climate change real and live in the Mediterranean, and I'm sure that we all know this. And I would like to say, first, I would like to start by citing public press. This is something that I read recently. It's about the horsemen of the apocalypse of the 21st century, and it's war, poverty, and climate change. We are expecting, because of the combination of these three causes, at least 140 up to 143 million people to be displaced by 2050, and this comes along with, of course, transmission of diseases and other things that have to do with the rapid change of populations in the world of today. And in relation to this, I would also like to say that one thing that has changed in relation to even 50 years ago is the speed in which we move, because back in 1918, it took 3 years to take the world around, but nowadays it only took COVID-19 20 days to be all around the world. So this is something that we also have to have in our minds when it comes to early warnings of epidemics, perhaps not applying explicitly in the case of vector-borne diseases, but in all diseases, I would say. You can expect a rapid spread through social networks to different places, and you can find diseases where you least expect them because of traveling. And then, of course, you can have sustainable environment of these diseases due to climate change and the increase of global temperature. So when it comes to what we see nowadays, we have climate change affecting the distribution of transmitted diseases through the intermediate hosts, and today we're going to discuss a lot about vector-borne diseases, and of course through water, and as I said before, through migration. I'm going to briefly give you an overview of West Nile virus in Greece. West Nile virus was first discovered in Africa, and it was endemic there, of course, but gradually it spread to Middle East, Europe, and Australia. And towards the end of the 20th century, it also spread to North America. Nowadays, we have a global expansion, and it's a vector-borne disease. It's there is a mosquito-bird transmission cycle where the natural reservoir are the birds, and the vector is the mosquito. Humans are dead-end hosts. Dead-end hosts. Which means that they don't. We cannot further transmit we're not a natural reservoir. We cannot further transmit the infection because we don't have viremia at a very high level. So mosquitoes cannot bite us and then further transmit the virus to others. And the same applies to other mammals, as horses, for example, which are also well known. And of course, climate change, vector adaptation, and urbanization are the three key factors that affect the spread of West Nile virus globally. And obviously, climate change is the far more important, interconnecting, of course, with the other two, which is vector adaptation and urbanization. So we had some sporadic cases in Greece since 2008, but I would say that the first epidemic has been recorded in 2010, and ever since we have fluctuating incidence. But we have a persistence of the virus. I can say that we're endemic. Every summer we have cases, and Greece, along with other Mediterranean countries, I have to say, is one of the highest ranked European countries in terms of annual West Nile virus incidence. And of course, there are key roles that affect this is environmental conditions. We have a very nice summer, but it's a very hot and very humid summer in several places where you can have the ideal conditions for enormous populations of mosquitoes, which of course carry the virus and can spread them to humans as dead-end incidental hosts, as I said before. So there are many places in Greece, and there are maps that you can find in the relevant publications where you can have lagoons, water concentrations with very high temperatures and a very humid environment, along with a lot of people doing holidays. And this is an ideal situation where you can have the spread of the infection from the mosquitoes to humans. I've created a small graph about the smoothed age standardized rate of West Nile virus infection in Greece and Europe as a whole from 2008 up to 2022. You can see with the blue-green line the age standardized rate for Greece, which is a lot, of course, higher than the overall age standardized rate for the European Union, including the UK. This is based on the reported rate from ECDC. The rate is never zero. We just have, as we said, the first epidemic back in 2010, and ever since we have a high number of cases in Greece. And of course, the standardized rate is also very high. And one thing that perhaps we should look at from this graph is that we also have a very low but steady increase of the age standardized rate in Europe. Okay, and this, of course, has to do with the virus, the disease, and the virus becoming endemic in more regions of the European region, starting, of course, from the southern parts and going more and more up to the north as the temperature rises, and there are conditions ideal for the establishment of the environment of the virus. So what do we do when it comes to the need of early warning for epidemics? I heard before Professor Rezza, he was asked about whether a specific early warning system exists about specific age categories. And of course, Italy has an excellent system of monitoring diseases that are vector-borne because of the history, of course, that they also have. And they do operate in a very well-established One Health approach, as Professor Rezza said. But I would like also to point out to a new epidemic early warning system that we had developed back in 2021, which came out, of course, of the COVID-19 pandemic, and this is where we first applied it. And it's a very nice tool that helps us detect early upcoming epidemic waves. I have to say here that the first idea came while we were sitting with my wife and watching volatility indices from the stock market, and this looked a lot like what an epidemic curve is. And this is how I began devising essentially this epidemic volatility index, which we first applied for the COVID-19 cases. And nowadays we also have it in our local university hospital in order to detect all around in real time the rise in flu, COVID-19, and any respiratory disease that may appear. And the reason for doing this is in order to be able to detect any abnormal rise early and notify the authorities and then see whether this is something that is expected, is not expected, is something new, or is not something new. And of course, this tool can be applied in any case, in any epidemic. For example, in the case of West Nile virus, we can apply this by sampling wild birds and see whether there is a rise in the deaths or the presence of the virus in dead wild birds. And this is known to be an early warning for an expected rise of cases in humans. The tool is free. We have software packages available. Everybody can download the packages and implement them on their own. And they can also see some training videos that we have available in YouTube. So this is from the recent application in the pulmonary hospital at the University of Thessaly, where you can see with the red dots when an early warning is issued. This is the case of respiratory infections in general. And another one that I would like to, and you can see that we do have for main waves an early warning, and here as well as here. And of course, the situation becomes a lot more clear in the case of infections that are seasonal, like West Nile virus, or in this case that you see here, flu, where the new wave of the flu is captured early, and we notify the hospital, and we know that we are expecting an increase when we have a red dot. And this, of course, in this case, helps the authorities to take action and be prepared for the upcoming epidemic wave of flu in this case. But of course, we can do the same for any virus, any infection that is of interest. And this is the essence of the tool that can be used in any case. And of course, everything is freely available online for anyone interested. They can download it and use it, of course. So this is what I would like to say, and thank you very much for the invitation once more.
Thank you, Professor Kostoulas. We have a couple of questions from the audience, and I just wanted to ask, with the early warning tool that you've introduced, you said it can be applied to many different cases. Someone specifically is wondering, how might you apply this to Scandinavian countries? And also, how many cases would kind of, flag that we have to start issuing a warning?
Okay, it's relative. First of all, it doesn't matter if you have 0 cases or few cases. The first thing that you start doing is monitoring cases of whatever you want to monitor. And if these cases start increasing or being volatile, then the tool, if the volatility in the number of cases is beyond a specific threshold, then it issues red dots. Consecutive red dots imply that a new wave is coming and that you should take action towards handling this, restricting this, doing what is necessary to do. Everything is available online and free from anyone that is interested to apply. And of course, we're happy to help if someone wants to apply this.
Perfect. Thank you so much. We really appreciate you sharing a case study based on Greece. And thank you so much for your presentation today.
Thank you very much.
All right, so our last case presenter is Professor Jan Semenza, who you have heard last week, and we're very excited to have him back again. He's an environmental epidemiologist with 30 years of experience in climate change and health, and he's associated with the Department of Sustainable Health at Umea University in Sweden and Heidelberg Institute of Global Health at the University of Heidelberg in Germany. So Professor Semenza, if you want to share your screen.
Thanks, Sarah. Can you see this?
Yes, you're good to go.
Excellent. Thanks. So I will continue the theme here on West Nile virus, and I will try to make the link to climate change, and I will take more like a European or continental perspective when it comes to West Nile virus outbreaks in Europe. Just to refresh your memory and come back to the definition here of West Nile. West Nile infections is a mosquito-borne zoonosis that is endemic in some parts of Europe, but almost epidemic in other parts. And you can see here that West Nile virus is transmitted among birds via the bite of an infected mosquito. And you can see that the transmission cycle circles around the birds here where a mosquito bites an infected bird that had been introduced into the environment. So this is a wild bird, a migratory bird that comes in the environment, and the mosquito picks up the virus and then transmits it to a local bird. And so you have this transmission cycle within these local birds. But then it turns out there are different types of mosquitoes that are called bridge mosquitoes. And in this case, these type of mosquitoes, they actually bite not only the birds, but also humans. And that's how they transmit the West Nile virus to humans. And we turn out to be incidentally infected. We are dead-end hosts. And so we cannot contribute to the transmission cycle of West Nile virus, but we do acquire the disease. And the virus can cause a disease that's called West Nile fever, which manifests itself with headaches, malaise, fever, malaise, but also vomiting, rash, fatigue, and eye pain. And so a number of symptoms that these people are afflicted by this particular virus. And it turns out that only 20% of individuals develop these type of symptoms. So 80% or so are asymptomatic. But less than 1% of people develop a disease that's called West Nile neuroinvasive disease. And in this case, they develop meningitis, encephalitis, or acute flaccid paralysis. And this disease is actually quite dangerous because 17% of these individuals with West Nile neuroinvasive disease can die as a result of that infection. Another issue on this slide here is also the potential transmission through SOHO, or substance of human origin, when the virus contaminates the blood bank or through blood transfusion or transplant of organs, where people can get affected with the West Nile fever as well. And here is the mosquito that's implicated in the transmission. This is a Culex mosquito. It's the vector for West Nile virus, but also the Uzutu virus, among others. And then the feature that this particular mosquito brings to the table is the fact that it has high seasonal abundance. So there are lots of these type of mosquitoes around, particularly in continental Europe. And it has high vectorial capacity for the virus, the West Nile virus. And then it leads to high field infection rate. So this is a very effective vector for West Nile virus. The clinical criteria for West Nile fever are, as I mentioned, a person with fever, encephalitis, or meningitis, which is kind of unspecific. But then, of course, laboratory confirmation needs to be carried out. And ideally, we like to isolate the virus from blood or spinal fluid, but that's very difficult to do. Obviously, PCR might be easier if you want to detect the nucleic acid of the virus in biospecimens. And then it turns out you can also look for IgMs antibodies, which are detectable after 3 to 8 days after the onset of symptoms. And these IgM antibodies that persist for 30 to 90 days after onset of symptoms. And then there's also a different type of antibody, the IgGs, and those show up pretty much at the same time as the IgMs, but they persist for years. And so the IgGs are more like an indication of past exposure, are not that confirmatory in a laboratory test on their own. So when it comes to the epidemiologic link, we would like to see whether a person has been exposed to mosquitoes, if they reside or have been visiting an area where there is transmission, or as I mentioned, if there is human-to-human transmission through blood transfusion or transplants. So that's the epidemiologic link. Then we also have the case definitions here. For example, a probable case is defined as an individual with clinical criteria with at least one of the two following criteria, like epidemiologic link or a laboratory probable case, like the IgG that I mentioned earlier. But then a confirmed case would be any person meeting the laboratory criteria of the case confirmation that I mentioned earlier. So what does the epidemic look like in Europe? And we have heard the situation of Greece. This one here is now the European perspective. The last season, 2023, we had more than 700 cases, the majority of them in Italy, but also Greece ranking here at the very top, with almost 70 deaths in the last season. Again, Italy and Greece ranking very high here with those deaths attributed to West Nile fever or West Nile virus infection. And this here is the map that's generated by ECDC on a regular basis. You can see that the majority of the cases are in the southern part of Europe, but we have also seen now an expansion into Northern Europe with cases occurring in Germany as well, highlighted with these red dots in Germany, as you can see. And if you look back a decade, you can see that several regions, or NUTS3 as they're called, these administrative units, how several units of these administrative areas have been impacted by West Nile fever outbreaks in the past. So this year is going back to 2013, and you can see the different color codings in orange and yellow for the different time periods here, 2022, and the longer period all the way back to 2013. Another aspect is also the outbreaks in animals, because it turns out that there have been a number of outbreaks in horses and in birds, as you can see here. And these data are collected by the European Commission through the Animal Disease Notification System. However, the important thing to remember here is that while a case in a bird is reportable by law in Europe, so it's mandatory to be reported, the monitoring of infections in bird is voluntary. So these maps that ECDC produces with these type of data is unreliable in the sense that it's not, the surveillance system throughout Europe is not as consistent as it is for human cases, obviously, and in part based on voluntary reporting when it comes to bird infections with West Nile virus. But you can see there is still a certain overlap with human cases, similar to the map that we had seen before. But as I mentioned, the surveillance system here is not as sophisticated as the one for human cases. So when you look at the epidemiology that has been published in the peer-reviewed literature, these are the drivers of West Nile virus. So we see that climatic factors like ambient temperature, precipitation, and relative humidity are factors that have been documented in the literature. And then landscape features such as the vegetation index or the water index are important, but then also the presence of the vector that I mentioned earlier of avian hosts. For example, we looked at migratory birds, and we looked at two different types of migratory birds, the ones that use an eastern migratory flyways and the western one. And we basically dichotomized it and were able to link these migratory birds to the West Nile fever outbreaks in Europe. But this is what epidemiology looks like. You can see there are almost 1,000 cases every year, with the exception in 2018, where there are more than 2,000 cases. And that particular year had experienced a rapid onset of the epidemic with many many more cases than we had experienced in the past. And so we basically trained the machine through this machine learning algorithm to process all these variables that I mentioned earlier in this XGBoost machine learning algorithm to identify risk factors or determinants of these West Nile fever outbreaks in Europe. And we ranked these drivers with these post-processing method, the Shapley method, in order to then come up with a predictive model. And we used out-of-sample data, like 2018 and 19, to test our model and evaluate the predictive ability. And this is work that was done by Zia Farok in Umea University in the lab of Joachim Rocklöv. And so what we see here is that these number of drivers of this disease, for example, the mean temperature of the warmest quarter was the strongest predictor, but so was the maximum temperature and the temperature seasonality, the mean temperature, and so on. So you see a lot of variables here that have temperature, a temperature characteristic that can potentially predict these type of outbreaks. And so we see that temperature is an overriding strong determinant of these outbreaks in Europe. And in fact, when we look at the bioclimatic or the climatic conditions in the previous year in relationship to the outbreak year that we're looking at, you can see that they explain something like 50% of the variance. And then the climatic data would be the data of the existing year of that current outbreak in combination with the environmental condition. They explain something like 35% of the variance. So you can see that we have a big explanatory capability here of explaining these type of outbreaks. When we then want to know what is the difference between a strong outbreak year like 2018 and 2017, if we compare these two type of outbreak scenarios, we can in fact see that the maximum temperature of the second quarter was statistically different between the 2018 year that was much warmer compared to the 2017 year, which was a normal outbreak year, but also the mean temperature of the second quarter was statistically significantly different in 2018 and compared to 2017. So this means that we can use this now as an early warning system, as was mentioned in the talk earlier. You can now differentiate that spring temperature as an indication that something is going on to assess the potential impact of that epidemic later on in the season. So this is an early warning system that we can build on in order to come up with predictive models. A paper that just came out last month looked at the historic climate all the way to 1900 and compared that to a climate without climate change. So this is a counterfactual baseline comparison where we compare the actual climate compared to a climate without climate change. And you can see that the ecologic suitability for West Nile virus infections has increased in our current climate if you compare that to a climate without climate change. So we can see that climate change contributes to this increased transmission of West Nile virus based on this paper that was just published last month. We now took that temperature relationship and pushed that forward in time on the climate change scenarios. And here you want to look at the 3 different columns for 3 different climate scenarios. So we look at the moderate climate change scenarios as opposed to a more extreme climate change scenario, which would be the RCP 8.5 on the right. And you can see how the yellow areas move from the southeastern part of Europe to the northwestern part of Europe. So we can see a successive expansion of the West Nile fever risk in Western Europe in relationship to climate. And so again, this is work that was done by Zia in our group at Umea, where we model an expansion of West Nile in relationship to climate change. And you can see this westward expansion. So it turns out that this risk when West Nile comes into new areas, this is a concern for blood safety because people are advised if they have been in a West Nile fever outbreak area not to go and donate blood because it could potentially threaten the blood supply. We propose here that the blood banks need to consider pathogen reduction technology to eliminate any pathogens in the blood banks, because once we have an expansion of these viruses in Europe, they can potentially threaten the entire blood supply and the blood banks. And so we need to think outside the box to cope with these rising risks in relationship to climate change. So what can we do about this? Obviously, we would like to develop a vaccine for West Nile fever. Unfortunately, there is nothing in the pipelines right now. So not a single vaccine has reached the stage 2 clinical trials at this point. There is no candidate in the pipeline that will reach market or be licensed anytime soon. And we can discuss the reasons why that is. But that's something we should consider, particularly in light of COVID, how fast we used RNA technology to do that. So that's something that's missing in this field. But we can resort to to monitoring climatic suitability. As I mentioned earlier, spring temperature can be used as an early warning system for later on in the season. So that's an early warning signal that we can use. We need to eliminate vector breeding if we see these climatic conditions to improve. We need to conduct seasonal surveillance to pick up potential cases. We need to make sure that people have screens on the window, that they use DEET as potential insecticide to keep these, repellent to keep those mosquitoes off their skins. And then obviously vector control by spraying. Then we need to set up a detection system to pick up cases, verification, notification, in order to then intervene rapidly to bring that epidemiologic curve down to minimize exposure of the population to West Nile. So in summary, we see that climatic variables are important determinants of West Nile fever transmission, along with a number of other vectors, but we see that the ecologic suitability has increased in our current climate due to climate change in comparison to a counterfactual non-climate change scenario. And we see in our modeling on the climate change scenarios that Western Europe in particular will be now facing larger outbreaks, in part due to climate change, because we see the climatic suitability will increase. And that has implications for our blood banks, because now suddenly new areas are at risk and they could potentially be threatened by an expansion of West Nile into new regions. And if you have any questions, here is my email, and I'll leave it at that.
Thank you, Professor Semenza, for giving us an overview of the European context. So we have some great questions coming in, and one of them going back, more into the West Nile virus, just understanding how long does the West Nile virus live in the human body? And also, can you expand on any particular vulnerable populations that might be at more risk in the European region?
Great, thanks, Tara. Great question. So that is a good question. The good news with West Nile is, in fact, that if you have been exposed to West Nile, you will develop lifelong immunity. So you will not get West Nile again. So that's the good news. The bad news is that there is no vaccine and there's no treatment for West Nile. And individuals that are elderly and potentially immunocompromised, they're at increased risk. And in fact, those are the individuals that will develop West Nile neuroinvasive disease, which has a case fatality rate of 17%. So that is of concern. So they need to make everything they can to keep those mosquitoes off their back.
Thank you. And also, another question is, do we see any trends in the increase of frequency of these less severe events in the European region?
I'm not exactly sure what less severe events refers to, but we do see more and more of these West Nile fever outbreaks popping up in more and more of these NUTS regions or administrative regions. Whether they are less severe, I don't know. There's still West Nile fever outbreaks that are a risk for susceptible individuals in particular.
Thank you so much. And do you know what type of risk communication activities might be taking place already in the European level?
That's a great question, because ultimately that's the only tool we have, right? We need to communicate with the public, and ultimately you cannot do anything in public health unless you engage the public. So I totally agree with you. Public communication, outreach to the public is essential for this type of outbreak control. We need to engage them in vector control activities, but also in protection, keeping people away from mosquitoes by eliminating standing water in the communities, putting up window screens and door screens to make sure that these people don't bite individuals that are susceptible to particularly West Nile neuroinvasive disease, which is potentially very dangerous.
Thank you so much for your presentation today. We really appreciate it, and I think everyone is very excited to have learned more about the West Nile virus.
Thanks, Tara.
So I'm just waiting for my screen to share, but I just wanted to go over. So thank you everybody for joining us today. So today's learning objectives, we were able to identify the connections between habitat, biodiversity loss, climate change, and infectious diseases. We were exploring how climate change is leading to increased risk risk to vector-borne and zoonotic diseases and their distribution patterns. We were discussing the impacts of temperature and climate modifications to vector, the reservoir, and the pathogen life cycles. And, we're learning about all these different health system adaptation actions and possibilities, such as these early warning systems. So again, thank you so much to our three presenters, Professor Giovanni Rezza, Professor Polychronis Kostoulas, and Professor Jan Semenza. As we conclude, we just want to remind everyone, please fill out the post-session survey. You can scan this QR code with your camera, and there is a link posted in the chat. This is really, really great for us to be able to receive feedback from you to make sure that the content is being tailored for what you want to know. And so thank you all so much for joining today. We hope you enjoy the session, and we'll see you next week. And, again, congratulations, you've been halfway there.